Okay, you guys, so I wanted to make a last video for the semester covering the memory interface. I know that not everybody's going to do it, but for those of you that are interested, here is a walkthrough again of what I presented in class with a little bit of extra information. So what we're doing is we're taking the design of our top level system, our SoC, and we're adding a block called the memory interface block. So on the left hand side of the memory interface block, those are the signals that go to the trammel blaze. On the right hand side is going to be the signals that leave our design and go to the memory on board. And you can see that there's 16 bits of bidirectional data and 23 address bits. Now, the design is not too complicated. We've gone over it in class. First, we have to keep in mind the interface signals that need to be supplied to the memory device itself. So it's a synchronous memory, but we're not using it in a synchronous mode. So you need to source the clock leaving our FPGA going to the memory and tie it to 0 inside of our design. So you want, when I say always 0, you want an output signal from our FPGA that's held at a constant 0. So the signal's clock, we can see down below ADV, pound, CRE, then the upper byte and lower byte enables. All of those signals should be sourced from your FPGA, but they should be held in a low state. Then we have the reset. Then we have the write line and the read line. The chip select is the select to select the memory interface block. Then we have the data in and the data out. Okay, so what's a little bit out of date for me? So the data in, data out are 16 bits now. That's going to our block, and then going out we have at the bottom the 16 bits of our DQ. So again, now that we've got the trammel blaze, we have a 16-bit interface. So our memory interface block now, we're communicating 16. I didn't update this chart, I apologize, but I updated the later charts. So let's go ahead and go to them. So what it turns out that some of you guys have Nexus 2s, some of you guys have Nexus 3s. And they all have the same memory device, the Micron device referenced above. And there's the fundamental block diagram. Now we're not going to have to worry so much about the internal operation of it other than interfacing to it. And we see again the signals that are required to interface to the memory. Now your responsibility will be to write and read the memory. And what this shows is the timing for a write cycle. Now the signals of interest is the address, the chip enable. In this case, since it's a write OE, so again the hash or the pound sign, they indicate low active signals. OE is the output enable, so that's what they've chosen to call read. So OE hashtag is a low active read. So what they're saying is you don't need to use the read when you're doing a write. And the write, where it says T sub WP, that's the write pulse. And then we have the data. We're sourcing the data when we're doing a write. And we are sourcing the address when we do a write. And the write cycle we can see from the following page, depending on which device is on your board, is either 70 nanoseconds or 85. So rather than having us all scrutinize exactly which device is on our board, it's safe for us all to assume that we have an 85 nanosecond write cycle. So what that's referring to is the TWC at the top must be at least 85 nanoseconds. So you have to be careful there as far as when you're generating the timing of the state machine out of the memory interface block. Then we have the read again, chip enable. We assert the OE signal this time. That's the read. The write enable is high. And then what happens is at a given period of time after we assert the read line, we see the valid data showing up on the DQ. So it's your responsibility, knowing once you've weighted the TRC on the top, so at least 85 nanoseconds, now you can assume that the data on the DQ bus represents the contents of the memory location you're reading. So what you want to do at that point in time, you want to then load that data into an internal register that you then make available to the processor. Again, the timing is the same, so we assume worst case we have an 85 nanosecond part. So the overall read cycle, TRC on the top, is 85 nanoseconds. So that means you have to wait at least 85 nanoseconds after you've asserted the chip enable and the read to make sure that you get the data you want. In our implementation, we have a 16-bit interface now with our processor, but what we still have is 8 meg of data. And the 8 meg, of course, we all know is 2 to the 23rd. So our address bus is 23 bits. So we're going to see that we have to have a couple registers to hold the address we're providing to the memory. The registers we're going to need, and we'll see on the diagram on the next page, is the write address 0, write address 1. Then we have to write the data that we want written to the memory. Then we'll have a read data register, and then we have to tell the state machine to perform a read or tell the state machine to perform a write. So these addresses are the address decodes of the Trammel Blaze. What we have right now is address 0 we're using for the UART. And so now we just follow right along. These addresses will be used for the memory interface block. So the design is comprised of basically these simple blocks. On the lower right, we see two registers, WA R0, WA R1. That's write address R0, write address R1. One of which will provide 7 bits to the address, the other will provide 16. Combined, they produce the 23 bits of address to our memory. There's a register, so we write address register 0 with write 1. We write address register 1 with write 2. And we write the data that we want to be written to write 3. Then when we want to perform a write and a read, so 5 is the read, 6 is the write. So if we set those 3 registers up like we just mentioned, we then would do a write to address 6. The state machine would detect the pulse on write 6, telling it to perform the write. Same thing if we set up the address, then we issue a write 5 that tells it to do a read. The state machine would then go through the read and then it load the data into the RD sub R register. And I didn't show here, and I should have. Out of the state machine should be a load signal coming here because it's the state machine's responsibility to know when to load the data into the read data register. Then on this side is the interface to the Trammel Blaze. The firmware, to be complete, we should print a little banner when we start up. Hello, my name is Bob, whatever, CECS 460. Every character that is received over the UART should be echoed still to the user. But starting at address location 0 in the memory, each byte should also be written out to the micron memory. And now that we have 16 bits, you could pack 2 bytes and then send it out. Remember, the micron memory interface should be written and read 16 bits at a time. We know that. When an asterisk is typed by the user, what that would mean is that all of the address, all the data that you've received, you should dump. So as you've been receiving characters, it should be written to the micron memory. When you receive an asterisk, you then dump it. And you should send a character in line feed first so that the dump data begins at a new line. Then after dumping the micron memory, you should then go back and wait to collect more data. Every time you send a new line to the UART, you should follow it with a prompt. And when you receive a backspace, you should automatically perform an auto delete by sending out a backspace space backspace. And what that would do, that would delete the character on the screen. Don't worry about going into the memory and modifying it. So that is the A1 overview of the firmware and the memory interface block. So sorry it's out so late, but let's see, maybe some of you will get it. If you're close, I'll be happy to extend this into the final week. So good luck, young people, and hope everything works out. Thank you.